Hi everyone, in today's tutorial, we will demonstrate how to use the shift register instruction to hold the GPS data received by the UART instruction from the Neo6M GPS module. The GPS time will be extracted and shown on a 6-digit 7-segment display. You will also learn how the set bit and clear bit instructions are used. The shift register consists of several variables specified in the instruction as required in a logic. Consider a shift register of 5 variables, register 0 to register 4, with the assigned values. Register 0, the input to the shift register, receives new values into the register on a rising edge of the room. A shift to the right of the initial values of the variables occurs. If there are no new values fed to register 0, its initial value will remain unchanged after the shift. Insert a shift register from the instruction menu. Double-click on it and rename it as Data. Assign 5 as the number of stages. Observe that the new variable name is now showing on the shift register instruction with the number 4. 5 variables, data 0 to data 4, created by the shift register instruction can be seen in the variable window below. Insert a contact and a one-shot rising instruction in the same room as the shift register. Insert an add instruction below the shift register with the destination and operand 1 variable as data 0 and the operand 2 value as 10. Insert a compare for less than instruction with value of data 0 less than 60. Simulate the logic and observe in the variable window that 0 is initially assigned to the variables data 0 to data 4. Each time the contact changes state from 0 to 1, the value of data 0 is increased by 10 and its previous value is transferred to data 1. Data 1 value to data 2 until the values are transferred to data 4 variable. The value of data 0 will stop increasing when it is 60. Thus, the unchanged value of data 0 will be transferred down to the other variables. To demonstrate how the shift register receives UART data, insert a UART receive instruction with a variable name of data 0 and a shift register with 6 stages and variable name of data in the same room. Insert 4 compare for equal instructions in series with a coil in another room. Assign their close-if variables as data 5, data 4, data 3, and data 2, and their equal values as characters A, B, C, and D respectively. Simulate the logic and sequentially impute the characters A to E in the UART simulation terminal. When E is imputed, the room condition becomes true, which indicates a match with the compare for equal instruction variables. Now, let us consider the Neo6M Global Positioning System model. This model can receive GPS signals from satellites in space to determine location, time, and speed. The model is made up of the Neo6M GPS chip with a UART communication port. Its default baud rate is 9600. The baud rate can be adjusted as required with the U-Box software, which we will consider in another video. It has an LED indicator that only starts blinking when a position fix is found. Otherwise, it is off. It has an EEPROM and a rechargeable battery that retains configuration data, latest position data, and clock data. It also has a patch antenna for receiving the GPS signal. It has the VCC pin, the GND pin, the TX and the RX pins. Since we will only be receiving the GPS data, Only the TX pin will be connected in our practical demonstration. The GPS module continuously spits out series of data every second. These data are called NMEA sentences of the National Marine Electronics Association. This tutorial is focused on the GPRMC sentence, which is Global Positioning Recommended Minimum Coordinates in full. The GPRMC sentence structure is as shown. It starts with the $sign GPRMC as the header. Each data in the sentence is separated by commas, with the first being the time in Coordinated Universal Time. The second is the status data, which is either V for navigation receiver warning or A for data valid. Then is the latitude, north-south, longitude, east-west, speed over ground in knots, date, and the checksum. Since only the time is required from the NMEA sentence, our focus will be on the first 18 characters with numbering from the status data. The hour will be extracted from the 11th and 10th position of the sentence, the minute from the 9th and 8th position, and second from the 7th and 6th position. Let us modify the previous example to receive and extract the time from the GPRMC sentence and display it on a 7-segment display. But first, set up this circuit diagram on your breadboard as in tutorial 10 for Arduino Nano, but having a 6-digit 7-segment display and the Neo 6M GPS module with its TX pin connected to the RX pin of the Arduino Nano. In the previous LD Micro program, select Atmel AVRO80 Mega 328 32-pin packages. Ensure that the baud rate is 9600. Set the PLC cycle time to 0.2. Change the stages of the shift register to 19. Make up the compare for equal instructions to 7 with close-if variables of data 18, data 17, data 16, data 15, data 14, data 13, and data 1, and their equal values of the $sign G, P, R, M, C, and A, corresponding to the header of the required data and the data status. This ensures that all other NMEA sentences are ignored except the GPRMC sentence. Insert another compare for equal instruction below data 1 with the same close-if variable and equal value of V. These two instructions ascertain that the time data is being received, which then enables the arrow data internal relay coil. With the internal relay enabled, the hour is transferred from data 11 and data 10 to H10s and H units, minutes from data 9 and data 8 to M10s and M units, and then the second from data 7 and data 6 to S10s and S units. These data are subsequently moved to the 7-segment display variables of digit 0 to digit 5. Another technique of transferring the display data to the 7-segment display will be used instead of the technique used in tutorial 9 and 10. It requires the direct transfer of data at once to all the port pins of the microcontroller. To transfer data to any hardware port, you must place a hashtag before the specified port variable name. To transfer data from the ports, place a hashtag before the port pin variable name, and then to set the port to be either input or output, place a hashtag before the variable name like so. To make all port pins of port A output, write all ones to hashtag thrice A, while to make them all input pins, write all zeros. Now, insert a one-shot rising instruction in series with two parallel move instructions that set port B and port C as output port with hexadecimal FF. In another room, insert a normally closed internal relay contact and an internal relay coil with the same name of OSC. The contact OSC will trigger a circular counter of 6 counts. The circular counter will sequentially switch on the 7-segment display via the transistors to display the required digit using the compare for equal instruction as before. The character to be displayed on the 7-segment display is then moved directly to port C with the 7-segment font converter instruction. Hexadecimal FF is first written to port B to turn off all the segments to prevent ghosting of the display. Then hexadecimal FE is written to turn on digit 0 for a common anode display. For a common cathode display, 1 will be written to port B. A similar operation is done to display characters on digit 1, digit 2, digit 3, digit 4, and digit 5. Using this technique, you don't have to assign output pin to each pins of the 7-segment display. Some additional instructions are required to display segment G of the 7-segment display. Since the ATmega328 used in the Nano does not have a port with at least 7 pins except port D, which have the RX and TX communication ports connected to pins PD0 and PD1. Port C, which the segment display is connected to, has the reset button of the Arduino Nano connected to pin PC6. Segment G is then connected to pin 7 of port D. A set bit instruction on #TRICE-D makes pin 7 an output pin. A clear bit instruction first turns off segment G. The 7th bit of port C is AND with 64, then compared with it to check the status of segment G before turning on segment G if it is true. This is done for the other 7-segment digits. Compile the program, build C solution, and call Flash MCU to upload the code into the Nano. The GPS module will start searching for the satellite signal. Zeros will initially be shown on the display. When the signal is being received from the satellite, the UTC time will then be displayed. Then much later, the LED on the module will start blinking every second to indicate position fix. Finally, this logic has been modified to set the time to the required time zone, set the hour and the minute alarm with 3 push button switches, and activate a buzzer when there is an alarm time match. First, this rung initializes the display by moving the characters GPS-TM to the display variables at the start before the GPS signal is received. A circular counter with 3 counts along with a normally closed contact X enter is used to change the display option from the time display to the hour alarm adjustment and the minute alarm adjustment. A normally closed contact is here because a pull-up resistor is used for the push button switch. The normally closed internal relay contact, arrow alarm, prevents the change of display when the enter button is pressed to reset the alarm. At this point, a compare for equal instruction is added to display the GPS time when the counter is equal to 0. The time data is first converted to the required time zone before it is sent to the display. Thus, these subtraction instructions convert the time from the ASCII to the binary data format. It is then converted to a single data for arithmetic operations with the multiplication and addition instructions. These addition, subtraction, and comparison for greater than instructions are used to convert the time to the positive offset time zone. Change this value to your required time zone. The adjusted time is then converted back to ASCII to be displayed on the 7-segment display. If your time zone is a negative number, you can delete this rung for the positive offset time zone and the open circuit instruction. This rung is then used to adjust the time to your required time zone. The GPS time with your set time zone is then sent to the 7-segment display with these instructions. For the alarm time, there is first the cyclic timer of 200 milliseconds with the internal relay coil that provides the push button repeat action when setting the hour and the minute of the alarm. Then 2 similar rungs for setting the hour and the minute alarm time. When the counter C-enter is equal to 1, the hour alarm time can be increased or decreased with X-Inc or X-Dec. The internal relay contact provides an auto increase or auto decrease of the hour count adjustment. This section ensures the count returns to 0 when 23 hours is exceeded, while this section ensures that the count goes to 23 hours when it is less than 0. When the counter value is equal to 2, similar logic of the hour adjustment is executed for the minute alarm time adjustment. The alarm minute and hour time values are then separated into their 2 respective digits and converted to the ASCII format, then sent to the display when the counter value is either 1 or 2. This rung provides a blinking action as a focus when either the hour alarm time is being adjusted or the minute alarm time. The set alarm hour and minute are then compared against the actual time, which enables the alarm set coil once via the one-shot rising instruction. The alarm reset is done in 3 ways, either by the X-enter contact, when the GPS data is being received at startup, or by 600-second turn-on delay timer. When the alarm is enabled, the buzzer is set to sound once per second by the cyclic timer. The rest of the logic is for the 7-segment display as it was in the last example, but for these normally closed internal relay contacts, arrow blink H and arrow blink M, that provides the blinking focus when the hour and the minute alarm time are being adjusted. For the pin assignment of the push button switches and the buzzer, X-enter contact is assigned to D2, X-Inc to D3, X-Dec to D4, and Y-buzzer to D5. When the code is compiled and uploaded to the Nano, the buzzer will immediately start sounding until the GPS signal is received. The enter button is pressed, or the 600 seconds reset times out. At the same time, GPS-TM is displayed on the 6-digit 7-segment display. Set the alarm by pressing the enter button once. Observe that the first 2 digits are blinking fast. Use the increase or decrease buttons to adjust the hour alarm. Press the enter button again. Then adjust the minute alarm on the 2 middle digits that are blinking fast. Pressing the enter button again will return the display to the current time. When the set alarm time matches with the current time, the buzzer will start sounding once every second. You can either allow the alarm to automatically reset after 600 seconds or press the enter button to reset it. In upcoming tutorials, the GPS model will be used to display location and speed along with the time. In our next tutorial, we will consider the quadrature encoder and the PWM out instructions. Please click on the like button below. It helps a lot. Drop your thoughts on the comment section. Consider subscribing to this channel if you have not. Hope to see you soon in our next tutorial video.